Welcome to the channel to Irrational. I'm Pranay Sharma, and in this video we are going to talk about the solutions of CS1 Paper A conducted by IFoA Institute in April 2024. We are going to go through the complete solutions. We are going to go through the detailed solutions of each question, but if you want the solution sheets, I will leave a number below in the description where you should WhatsApp or Telegram your email ID and ask for CS1 answer sheets. We are going to email you the same. If you find any mistakes in the solution, please do comment below. I'll reply as soon as possible, and I'll pin a comment with any mistakes that might be there. So please check them out too. So without any delay, let's get started. Question number 1. The following table shows the possible realizations x. For the random variable x, the probabilities of these realizations and the conditional expectations and variances of a random variable y conditionally on x. First part, identify which one of the following options gives the correct value of the unconditional expectation of x and y. So for unconditional expectation of x, we'll just say x into probability of x in all three cases and add them up. And for unconditional expectation of y, it's just going to be expected value of y given x. So you will just multiply these two, that is probability of x and expected value of y given x, and add them up to get the expected value of y. So that gives me expected value of x is 20 and expected value of y is 6. That is option A. Whenever you are asked an MCQ question, you just have to specify the option, nothing else. Second part, calculate the unconditional variance of y. For the unconditional variance, you will require expected value of variance of y given x and variance of expected value of y given x. This will be very simple. We have variance of y given x, you need expectations, so you will multiply with the probabilities of x and then add them up. But for the variance of expected value of y given x, you will assume that expected value of y given x is another variable, so you want expected value of that variable square minus expected value of that variable whole square. So this part we already know, that is 6. But this part you will have to find again from the table. From here you will square these values and multiply with the probabilities and then add them up. So that gives you 11.2, and final answer of variance of y is going to be 12.8. Let's go to question number 2. Question number 2, the preparation time in minutes for coffee in a popular coffee shop has the following density. So this seems very similar to a gamma distribution. Show that this density can be written in the form of an exponential family. Also determine b theta, a phi and c y phi. First thing, you will put exp everywhere. So you have log 8 minus log m raised to 4, where raised to 4 comes out. So I'll have 4 log m. You have log y, this will be plus, and then minus 4 y by m. Now you will have to rearrange this in the exponential family form. So that is what I have done here. So minus 1 by my and 1 by 4 goes to the denominator, and I have minus log m. So clearly my theta is minus 1 by m. B theta would be log m. You can convert that into minus log minus theta. A phi is 1 by 4 and the rest is just c. If you were able to identify that this PDF seems to be very similar to a gamma distribution, then making the exponential family becomes very easy. Let's see the second part. Two models A and B are proposed for the parameter m, the mean preparation time for different types of coffee. Model A 1 by m is ui, where I is 1, 2, 3, 4. Model B 1 by m is u for I is equals to 1 and u plus v for 2, 3 and 4, where these corresponds to different types of coffees. Second part, comment on the mean preparation time for different types of coffee proposed by the two models. So we'll comment in model A, each type of coffee has a different mean, hence model A has 4 parameters. In model B, there are two distinct mean preparation times. Coffee type 1 has 1 by U, whereas coffee type 2, 3 and 4 has 1 by U plus V. Hence the model 2 has 2 parameters. Let's go to the next question. Question number 3. X and Y are distinct random variables with the joint distribution given in the table. So we have the joint distribution here. Identify which one of the following options gives the correct value of the conditional expectation Y given X is equals to 2. So first you will add these up to get X is equals to 2 probability. That is 5 by 10 or 1 by 2. Then for expected value of Y given X is equals to 2, you will say Y is minus 3 into this probability minus 2 into this probability minus 1 to this 0 into this. Add them up and then divide by this 1 by 2, that is probability of X is equals to 2. That gives me minus 1.6, that is option C. For the second part, determine the conditional expected value of X given Y for each value of Y. So first we will require probability for each one of those Y. That means you will just add these up. That gives you probability of Y. And then for expectation, you will just say this into this plus this into this divided by probability of Y is equals to minus 3. That is what you will do for each one of these Y's. And that gives me expected value of X when Y is minus 3 as 4 by 3. When Y is minus 2, it is 2. When Y is minus 1, I get 1. And when Y is 0, I get 2. So the third part, calculate the expected value of X using your result from part 2. So we want expected value of X as expected value of X given Y. This is what we want to use. We have all of these values. We want now expectation of that. So it will just be this into this plus this into this plus this into this plus this into this, and that gives me 1.5. Let's go to the next question. Question number 4. Consider random variable X, Y and Z, each of which has variance equal to 1. Suppose that covariance of X, Y is 0.9, covariance of Y, Z is 0.8. Let A be X is minus 0.9Y and B be Z minus 0.8Y. Calculate the variance of A, variance of B. A is X minus 0.9Y. We can split the variances. We'll get variance of X plus 0.9 square variance of Y minus 2 times 0.9 covariance of XY. We'll substitute those values and we get variance is 0.19. Similarly, for B, this will split into variance of Z plus 0.8 square variance of Y minus 2 0.8 into covariance of YZ, and then substituting values I get 0.36. So second part, show that covariance of AB is equals to covariance of XZ minus 0.72. Covariance AB, we'll substitute both of them and then give individual covariances. So we get XZ and minus 0.8 times XY minus 0.9 times YZ and then plus 0.8 times variance of Y. That is covariance Y, Y gives me variance. By substituting all of these values, we'll get covariance of XZ minus 0.72. Third part, show that the covariance of XZ is greater than equal to 0.458. You can even see they have given you hint here. Use the fact that correlation AB is greater or equal to minus 1. So we'll use that correlation of AB is greater or equal to minus 1. Then just convert that, we'll get covariance AB upon under root of variance A, variance B. Now we'll just substitute these values and then rearrange them. We get covariance AB is greater or equal to 0.458. Let's see the next question. Question number 5. Let sample of X be independent observations from a distribution of a random variable X that the parameter U that has parameter U. Let f of U given sample of X be the posterior distribution of this and G sample of X be an estimator of U. State two properties that the loss function should satisfy, and then consider this loss function. Verify that this loss function satisfies the properties in part 1. So the two properties of a loss function are: the loss function should not be negative for the range of the parameter, and there should not be any discontinuity in the loss function. So we'll use that loss function. So when U is less than G, then this loss function is positive. Similarly, when U is greater than G, it is positive. So we have that it is not negative. Similarly, if I check from one side, I get G minus U is 0, and here U minus G is 0. When U is equals to G, that means we have these function as continuous as well. So the loss function is non-negative and continuous for the range of parameter. Spelling mistake, it should be range. Third part, identify which one of the following option gives the correct expression for the expected posterior loss. This was very straightforward. When U is less than G, that means G going from U going from minus infinity to G, the function is G minus U. That means these are all posterior functions, so no problem there. And then plus, when U is greater than G, that means going from G to infinity, 3 U minus G is the function. So the option is D. Identify which of the following option gives the correct quantile for the Bayesian estimator B of U under this loss function. They have even given you hints here. All we have to do is differentiate this function with respect to G, equate it to 0 to get the probability here. So differentiating the expected loss with respect to G, here you can see you get just 1, and here you will get minus 1. Equate them to 0. Rearrange, this is just probability less than G, this is probability greater than G. So probability U less than G for this given sample of X, you will get is 3 by 4, that is 0.75. That is option C. Let's go to the next question. Question number 6. A lecturer wants to investigate the proportion P of students in a large class that are in favor of online lectures. The lecturer conducts two small surveys where students can vote in favor or against online lectures, and the results are as follows. So we have sample size and in favor. The two samples are assumed to be independent, so you can assume them to be binomial. The lecturer does not initially have any prior information about the proportion P and assumes a suitable uniform distribution as the prior distribution in order to estimate P. State the parameters of a suitable prior distribution for P, justifying your answer. So we'll say as the probability ranges from 0 to 1 and lecturer does not have any prior information about the proportion, hence P will follow a uniform distribution between 0, 1. Second part, determine the Bayes estimate of P under the quadratic loss function. So we'll have to find the mean and of course the posterior distribution. We had a uniform distribution, hence prior is going to be just 1. For likelihood, we had two samples of binomial. So P raised to success, 1 minus P raised to failure. Then again P raised to success into 1 minus P raised to failure. I have taken proportional to, so that is why I have removed all the constants. So multiplying these two, I will get the posterior. So I get P raised to 13, 1 minus P raised to 17. This is nothing but a beta distribution where this is alpha minus 1, this is beta minus 1. So I get 14, 18. The Bayesian estimate is nothing but the mean of the posterior distribution. So mean will be alpha upon alpha plus beta. That gives me 0.4375. For the third part, the lecturer later decides instead to use a beta distribution as the prior with the parameters a and b, where a is equals to 2b. Third part is determine the new Bayes estimate of b under the quadratic loss function in the terms of parameter b. Now our prior is going to change. It comes from a beta distribution where alpha is 2b and beta is b. Likelihood is exactly same as before. We'll multiply, and this is going to be our posterior. So the beta distribution will have the parameters 13 plus 2b and 17 plus b. So the Bayesian estimate, that is the mean, is going to be 13 plus 2b upon 30 plus 3b. For the fourth part, the lecturer is interested in obtaining a posterior estimate involving low uncertainty. Determine whether the estimate in part 2 or part 3 produces a posterior estimate with lower uncertainty in the case where b is equals to 1. So we'll comment accordingly. When b is equals to 1, we have slightly more prior information in part 2 than no prior information in part 1. The value of b is influencing the posterior mean, hence there is less uncertainty in part 2. Let's go to the next question. Question number 7. First part, explain what is meant by conjugate prior distribution. So you just have to write the definition. Then let x1 to xn be independent and identically distributed random variables from the Poisson distribution with the parameter m, and m follows a priori gamma distribution with a probability density function given by this. So we have a and s as our parameters. Second is show that the prior distribution is conjugate for m. So for the definition, when prior distribution is same family as posterior distribution, the prior distribution is called as the conjugate prior distribution. Now we will show that for gamma distribution, m raised to a minus 1 and e raised to minus sm. Likelihood from Poisson distribution, I am leaving out the constant, that is the denominator. So m raised to summation xi and e raised to minus nm. For posterior, we'll just multiply these two and we get m raised to summation x plus a minus 1 e raised to minus n plus m into m. So you can compare it with the prior distribution, and that is nothing but a gamma distribution. So we get our posterior is a gamma distribution with the parameter summation x plus a and n plus s. Hence, the prior distribution is conjugate for m. Third part, determine the mean and the variance of the posterior distribution of m. So we'll use the gamma distribution, mean and variance, that is alpha by lambda and alpha by lambda square. Okay, and the fourth part, comment on how the prior distribution affects the posterior for large sample size n. So here are the expected value and variances, and we'll say for a large sample size n, comparatively the parameter s will not influence the posterior distribution, but the parameter a will have an influence on the posterior distribution. So because n is large, s will not have a big say in the denominator here, but a will definitely influence both of these expected value as well as variances. As a increases, the mean and the variance of the prior distribution increases, and the same with the posterior distribution. Hence, the mean prior position affects the posterior distribution, and uncertainty, that is the variance of prior distribution, affects the uncertainty of the posterior distribution. For the fifth part, consider now the parameter 1 by m. So A is identify which one of the following option gives the prior mean for the parameter 1 by m. So m is following a gamma distribution. We'll use that to calculate the expected value of 1 by m. Expected value of 1 by m into the PDF dm. When you simplify this, when you remove one of the m's, you'll get m raised to A minus 1 minus 1 because I want to make it exactly same as the gamma distribution here. So instead of A, I have A minus 1. So I will create that here and here by removing S upon A minus 1. So this is nothing but the PDF. So this is nothing but PDF of a gamma distribution A minus 1 comma S. So this part will just become 1. So the mean will become S upon A minus 1. That is option D. B part, identify which one of the following option gives the posterior mean for the parameter 1 by m. So for posterior, just your S and A value is going to change when you substitute from the posterior distribution, and I think A will be your correct answer. Let's go to the next question. Question number 8. In a particular year, the members of a regional oil organization decides to increase the production of oil. The analyst wishes to model the effect of this increase on the market price of oil and recorded the monthly average volume produced X in liters and its price per liter, that is Y, for the 8 consecutive months. The data are summarized as follows. So they have given SXX, SXY, and these we can use to calculate SYY. You have to calculate the Pearson's correlation coefficient between X and Y and then comment on your answer to part 1. So we'll calculate the SYY and then R. That turns out to be minus 0.87104. We see a high negative relationship between the monthly average volume produced, that is X, and its price per liter, Y. For the third part, a second analyst thought that converting the volume to cubic meters as Z is X by 1000 would make the computation more efficient. Third is write down SZZ expressed in terms of SXX. They just said write down, so I'm not expecting them for us to show the whole conversion, but if you want to, you can. You can show that SXX is summation x square minus summation x the whole square by n. So if you put Z as x by 1000, you will have upon 1000 square here and similarly upon 1000 square. So clearly it would be upon 1000 square here as well. So SZZ would be SXX upon 1000 square. I have also written for SZY just so that I don't get confused later on. Fourth part, calculate the new Pearson's correlation coefficient between Z and Y. Fifth, comment on your answer to part 1 and 4. So you would see basically there is no change. I have converted my SZY and SZZ into XY and XX, and it is nothing but the same as the previous R. So the comment would be the correlation coefficients are not affected by change in scale. This is called change in scale, dividing or multiplying by a constant value. Hence the correlation coefficients are same in part 1 as well as 4. Sixth part, determine the least square fitted regression line between Y and Z given that summation Z is 0.16. So first we'll find Z bar and Y bar. Using that we can find the beta hat and alpha hat. We are getting minus 6.71136 and alpha hat would be 22.7592. So we can make the regression line. Determine a 95% prediction interval for the price of oil when the oil production is 1.5 meter cube based on the observed data. Prediction interval is just confidence interval for individual response. We learned that in R programming. So to find the confidence interval, first we'll require the sigma hat square. Then we will calculate the individual value y hat 0 by substituting in the regression line. Then we'll calculate the variance for that individual response. Remember that we add a sigma square for individual response. Then for calculating the 95% confidence interval, we'll have y hat plus minus the t distribution with the degree of freedom of n minus 2 under root of variance of the response. So the confidence interval I get is minus 12.657 to 38.041. Let's go to the next question. Let's see the last question. A small vehicle repair shop 1, has recently merged with another nearby vehicle repair shop 2, and the owner wishes to analyze the number of customers that visit each shop. The owner has recorded the following data over the past 30 days. Calculate the sample means of the number of daily customers for each repair shop. So we'll just say this total divided by 30 for both of them. Then next, the owner believes the number of customers arriving at repair shop 1 and repair shop 2 per day follows separate Poisson distribution with the unknown parameter K1 and K2 respectively. Second part, calculate a 95% confidence interval for the difference between the parameters K1 and K2, stating any assumptions you make. Assumptions: both the sample have large sample size and both samples will follow normal distribution using central limit theorem. We are assuming this because actually they are both following Poisson distribution, so we have to assume that they have large sample size. Only then we can convert them into a normal distribution using central limit theorem. So I have shown that here and then calculated the confidence interval for K1 minus K2. So just have x bar 1 minus x bar 2 plus minus z 2.5 under root of the variance, that is K1 plus K2 by 30. We will take the hats, that is the estimates for this K1 and K2, that is x bar 1 and x bar 2. So the confidence interval would be minus 0.0536 to 4.987. So the 0 does lie between this confidence interval, although it is just on the border. Third part, test at 5% significance level whether K1 and K2 are equal. You can use this confidence interval because that is also at 95% confidence, or you can do the whole hypothesis testing again. Both are fine. I've just used this confidence interval. So we'll say as 0 lies in the 95% confidence interval, at 5% level, there is no significant difference between K1 and K2. That means K1 and K2 are equal. For the fourth part, the owner later believes it may instead be more appropriate to consider the recorded data as being paired. Explain why it may be more appropriate to treat the data as paired. The number of customers that visit the repair shop may be dependent on the type of days, that is, days like Sundays and other holidays may experience more customers. A paired data will not be affected by such fluctuations. The present data collected for both shops is for the exact same days, hence it may be more appropriate to treat the data as paired. Fifth part, the sample standard deviation of the paired differences has been recorded as 6.55. Test at 5% significance level whether K1 and K2 are equal, assuming the data is paired, stating any additional assumption you make. So here I would say the assumption is the number of customers for both shops follow normal distribution. That means I am assuming from the beginning those distributions are normal. Then we'll calculate the D bar, that is just x bar 1 minus x bar 2, and HD is given as 6.55. Our hypothesis is that mu D is 0 or mu D is not 0. Our test statistic for paired data is very straightforward. We will substitute and the statistics we'll get is 2.06267. The p-value is going to be 2 times probability T29 greater than the statistic, that is just below 5%. So at 5%, we have sufficient evidence to reject H0. There is a significant difference between K1 and K2. Sixth part, comment on your answer to part 3 and 5. So because both of these are contradicting answers, they are asking us to comment on it. We have 4 marks. In part 3, at 5% we conclude that there is no difference, whereas in part 5, at 5% we conclude that there is a significant difference. There are multiple reasons to consider for this differences. First is, for this data, paired test is better approach as mentioned in part 4. So second is, the assumption of normal distribution and large sample may not be appropriate as the number of customers follow Poisson distribution is positively skewed. Assumption of normal distribution may skew the result when statistics are near the ends. Last point, in both cases, the p-value are nearly 5%. In such cases, conclusion should not be at 5% level as small changes in sample or other set of samples may change the conclusion. We are saying that the statistic or the p-value in both cases are very near to the 5% mark. So the conclusion should not be done at 5%. It should be done at 1% or maybe 10% or some other percentage. That ends our paper here. Overall, the paper was a little bit moderate. You might have found it a little bit lengthy because we had to think more for most of the questions because they were easy, but they were different from what we are used to. But the questions were easy, so most likely a lot of people will score well in this examination. The passing mark will very much depend on paper B as well, for which I'll be making the solution soon. I'll leave the link down in the description when I upload the paper B solution. If you found this video helpful, do like, share and subscribe. I'll see you in the next one.